coming. My talk, as the title suggests, this is a talk about attacking a security product, specifically Fortinet, which is a very interesting one. I chose to research about Fortinet FortiWeb. This is their web application firewall appliance. So without further ado, let's begin. So who am I? My name is Aviv. I'm a vulnerability researcher at NG Research, a CTF developer, and a proud owner of the domain poner.gg. This is my blog. And what is in the agenda for today? We'll start with a quick intro, and I will talk about the motivation behind the research, environment setup, and then we will dive into the first bug, which is an out-of-bound read. And this out-of-bound read eventually turned out to be a full authentication bypass, so we will also see that. And then we'll talk about the second bug, which is a pre-auth RCE. And then finally, we will discuss about some of the reverse engineering process, tooling, etc. So security appliances, why? Well, first of all, they often run as root, as funny as it may sound. The second reason is this is a single point of failure. One bug here bypasses all downstream controls. And the third reason is that I noticed there's a certain trend or pattern on Fortinet products. And another reason that is personal is breaking security appliances can be fun, because this is the device that was supposed to protect you, but eventually, because you put it in your organization, this is the reason you got hacked. So it's pretty funny. Now regarding the trends. As you can see, there's a growing trend in remote code executions on Fortinet products. In 2023, we had the legendary Zordigate. So for some of you who know that, it was presented in DEF-CON, Las Vegas. We had FortiJump in 2024, and in 2025, I joined the party. So now that we had a quick introduction, let's talk about the environment setup. FortiWeb has 3 types of deployment. The first one is a physical device. Second one is a managed cloud deployment. And the third one is private cloud deployment, which is another word for just a VM file that you can spin up locally. So for obvious reasons, I took the third option. And because you can, just like I said, you can spin it up locally and inspect it. So after you boot the VM and you see that everything is working, the first thing you do is to get the file system. So to get the file system, you grab the VMDK file, list the partitions on the VM disk. By the way, the VMDK file is the virtual machine disk. You list the partition, you mount dev-sda1, and rootfs will wait for you there, unencrypted, ready to inspect, which is very nice, very friendly for a researcher, because in many products, especially their other products like FortiGate, the file system is encrypted or signed or stuff like that. But in this case, it wasn't like that. So this was a good sign that we're going to find the vulnerabilities. Right. So after we got the file system extracted, we need to map the attack surface. So the main 3 things I needed to map the attack surface were: the first one is to understand the file system layout. So for the purpose of this talk, what you need to know is that in the bin directory, there's an HTTPSD binary. There's also a CGI bin directory accessible from the web. The second thing is to identify the Apache setup, because this HTTPSD binary is actually an Apache server. So the configuration of this Apache lives at /migadmin/httpd.conf. The Apache server is listing on port 443, and custom Apache modules were bundled with the Apache build. And this is the important part because all the vulnerabilities were found in those Apache modules. And the third thing is RE tooling, which I said in the introduction that we will discuss about at the end of the talk. TLDR, I made a tool that helped me to reverse engineer, that helped the reverse engineering process for me to be more efficient. And like I said, we will look at it after we discuss about the bugs. Okay, so we had an introduction. We discussed about the setup. We extracted the file system. And now we will start to discuss about the first bug, which is, it started as, like I said in the beginning, it started as an out-of-bound read. My goal was to leak memory. I couldn't leak memory. I tried harder, and then eventually I found out that it's even better than I thought. It turned out to be an authentication bypass. So we will see the entire thinking process of that bug, discovery, and exploitation. Okay, so how FortiWeb authenticate its users? The FortiWeb admin portal authenticate the client with a session cookie. I guess this is too small so you can't see, but in the next slide we will zoom into it, so it's okay. Now, speaking about that cookie, this cookie is composed of 3 parts. The first part is called era. I don't know what it is. I don't care. But it can be 0 or 1. The second part is payload. This is encrypted data that contains session information, such as your username, role, and other general purpose metadata. The third part is called auth hash. And the auth hash is an HMAC SHA-1 hash, contains the encrypted ciphertext of payload, signed with the same secret key that used to generate payload. So in other words, the payload part is ensuring confidentiality, that the user won't be able to see what is inside the session metadata. And the auth hash is intended to guarantee integrity, so the user won't modify anything in his session cookie. Now, the authentication to the /API v2 routes are protected using a custom Apache module handler. As you can see here, they are using, can you see my mouse? Oh, great. They're using the location directive. I'm sorry, they use the location directive on API v2, and everything that goes through API v2 will trigger that handler. And this is, like I said in the beginning, they have a custom Apache modules, so we will see how we can find the implementation of this specific handler. Right, so looking at AP pre-linked modules, this is an array, by the way. The part of the Apache ecosystem, this array contains a list of all the pre-linked Apache modules that are bundled within the build. So if you look at it, in the beginning you will see a lot of familiar modules, a lot of popular Apache core modules like HTTP, UnixD, dir module. But if you keep scrolling down, you will see one module that stands out. And guess what? This is exactly the one that we saw earlier from the configuration. This is a FWB CGI module. Now, it's hard for me to say FWCGI, so I would say FortiWeb CGI, okay? Because this is the real meaning of, of those letters. So now we will discuss about the FortiWeb CGI module and the way that it registers itself to be part of the request processing of Apache. Because now we saw the configuration part, but under the hood, there's an extra logic that is executed Let's just call it like that. So, like we saw in the previous slide, we have this array. One of the entries is 40Web CGI module. And what it is actually a pointer to a module descriptor. I'm not sure if descriptor is the right word. This is why I put a quote on it. This module descriptor is specifying some things about the module. This is a C data structure, which is part of Apache runtime. And one of the fields inside that structure is, as you can see in the yellow part, is 40Web CGI module register hooks. This is a function pointer pointing to a function that, as the name suggests, it registers a hook. And it's called once on startup by Apache. And what it does, it registers a callback function. And from that moment on, Apache will know that every time there's an incoming request, Apache will trigger this callback written by Fortinet developers. So let's look at what is inside that handler, right? So the main parsing logic is in cookie-val unwrap, and it's reachable from our callback that we saw in the previous slide. You can see here, this is the module structure, all the way to register hooks, and syncs down all the way to cookie-val unwrap. So now we will start talking about the way that the product parses the cookie. The first thing it does is that it uses smprintf on scanf to capture the values from the cookie format and put them into variables. After it captures them, it's verify the HMAC signature of the auth hash and decrypt the data inside the payload. And it's doing that by picking a secret key from the memory based on the era field. Now remember the era that I told you before that I don't know what it is, I don't care what it is, but all I know is that it can be 0 or 1. The vulnerability is there. As you can see, there's an out-of-bounds read via this era parameter. So my initial thought was, great, we have a memory leak. But it's not quite like that, because this is an out-of-bound read, a blind out-of-bound read. What it means is that, yes, you trigger out-of-bound access, but the value that is accessed out-of-bound never comes back to you in the response. So this is frustrating. And at this point, I was frustrated because I really wanted to leak memory, and I didn't care about other scenarios because I like memory corruptions. And then came the desperation, and when I almost gave up, I tried again, like I said in the beginning of the talk, and I found out that it can be a logic bug. Just like, yeah, no, unless we can turn this primitive from a memory leak to a logic bug. Looking again at the function's logic, I figured that we control the secret key that the server will use to verify the token. So if we can predict the bytes in memory after the secret keys array, we might force the server to use a secret key that we know in advance. Only if we know what is after this array, because we triggered out-of-bound access. So you must be asking yourself, what is found after the secret keys array? That's a good question. Nothing. The answer for that is nothing. As you can see here, this is a memory dump of the like during runtime of the array, and what it means is that if you use era 0, this is the secret key that will be used. If you use era 1, this is the secret key. But if you trigger the out-of-bound, this is the secret key that the application will use to verify the token signature and decrypt the payload. So now that we know what we can do with this, we start to build the exploit components. The first thing we're doing is to create our own helper functions to generate a token. So what you see here is just the same logic that Forty implements in their modules, only in Python. The first function is for decrypt, which is intended to generate the value of payload, and the second one is Forty sign, which is intended to generate the value of auth hash, and a third function that wraps around both, which is called Forty cook, and Forty cook, what it does is that it calls for decrypt, Forty sign, and just combines everything together into the format that we saw in the beginning, the format of the cookie. And of course, also triggering the out of bound into the null region that we saw earlier. Right, so I think this part, right. Okay, so now you're going to see the demo. I hope it works. No, the exploit is too quick. 1 second. I wanted to look, that you will see the phases. Okay. Less, okay. Anyway, what you can see here is, you can see here the cookie, the era 8, and the payload that we ourselves encrypted. And I think that you can't see here, but it's past the right part of the screen. There's also the auth hash and everything. And we send a request to an endpoint called system status. Yeah, I don't think you can see the name of the endpoint. It's called system status. And we get a 200 response. And we also get the response, like the JSON response. And this endpoint starts with API v2. So like we saw in the configuration earlier, it goes through the Apache module. So this endpoint is behind authentication, and we bypassed authentication. Right, and we're back. This is the typical flow of exploit development, by the way. And another thing is that it was also caught exploited in the wild. I saw this on Twitter by some company called Diffused. They have honeypots, and they told me that they see a lot of attempts to exploit this specific bug since I reported it. Like, it was closed, and then a few days later, it's just spiked. So this is interesting. Okay, so a quick recap. We have a working research environment. We talked about this. We presented the out-of-bounds read. After that, we discussed how to turn this into authentication bypass. And now we're ready to talk about the second bug, which is a pre-auth RCA. So just like before, we start from the Apache configuration. Another interesting Apache handler was found in the Fabric connector feature of the device. Again, I don't know what is Fabric connector. I'm a hacker. For me, it's input-output. But as you can see here, they use the location directive and the set handler directive to specify a specific handler to a specific route. So let's see what is implemented in that route. The handler has a function called getFabricUser by token. It is vulnerable to SQL injection. As funny as it may sound, unauthenticated SQL injection. And it's reachable from the handler's callback. FDS callback is the callback that the module registers for this specific handler. And as you can see here, you have the module, FDS callback, and it syncs down all the way to the vulnerable function. So now let's look at the logic of it. The access check function is parsing user-supplied headers, such as authorization. And the authorization header goes into the char token variable as is without any validation or sanitation. And later, this token variable is passed to the vulnerable function. And now we will, in the next slide, we will look at the vulnerable function itself. So this is how it looks like. In getFabricUserByToken, the session token is concatenated to an SQL query, no prepared statements or anything like that. Surprising. And do I have anything else to say about this? No, we can continue. Okay. So we have an SQL injection, as simple as it looks like, right? So our goal is to leverage that to achieve RCE. And we can do this using SQL's into-out file query. For those of you who don't familiar with SQL, SQL has a special, I don't know how to say it, special statement called into-out file that you can use to write files. So for example, in this example query, you can see select hello into-out file, and this will trigger a file write with the contents of hello. So our plan is to write a web shell to the CGI bin directory and profit, right? What could go wrong? But we have some limitations that we need to overcome. The first limitation is that we have character limitation. As you saw before, earlier in the screenshot, yes, they use scanf, but they use a prefix of 128. And it might seem like a lot of characters. It is a lot of characters. You do have a range of, you can do a lot of things with 128 characters, but not writing an entire web shell. Because it's not just 128 characters for the file you write, it's 128 characters since the authorization header begins. So it costs you extra characters in order to just trigger the injection. Another obstacle, the second obstacle, is that we cannot use space character because the S modifier, if you use the S modifier, anything after space, it just stops receiving. And the third obstacle is that, and this is probably the most painful one, we need a way to execute chmod on our web shell, because even if you can write a file to CGI bin directory, which I did this in the beginning, it didn't work when you try to access it, because mod CGI wants it to be in mod CGI wants the executable bit set on that file. So you need to execute chmod before starting to use the web shell. So now we will break down those three obstacles one by one. The first one is the easiest one, space character limitation. To overcome that, we just use SQL comments and not spaces. You can see, like, if you want to do select 1, 2, 3, you just, instead of space, you can type in an SQL comment, an empty comment. After I completed the exploit, I had a friend that told me that, another very creative solution to avoid, with a lot less characters. You can type tab, just so you know. This costs you 4 characters. Tab is 1 character. Character limitation. This is the second obstacle. Like I said, we are limited to 128 characters. So to overcome that, in our injection, we create a temporary SQL table, and then we send multiple requests to append more and more characters to the table until we build the full web shell string. And then finally, after we filled this table with the entire file that we want to write, the contents of the file, we trigger this. We trigger another injection, but this time with with an into-out file statement that we saw earlier. And instead of target path, obviously we will write the path of the file that we want to write. And this gives us arbitrary file write primitive. Now we can write a web shell to CGI bin directory. I called my web shell x.cgi. And the third obstacle, which is the last one, as I said, the most painful one, it required me to be very creative to find a solution for that. And it's to make our web shell executable. The web app has a CGI script at CGI bin. It's called ML draw. Again, I don't know what it is, but it was useful for me because we have access to it unauthenticated. And this script has an import pylab line in it. So we can use the file write primitive to write a file to this path, var log lib python pylab.py, the following content: OS system, chmod. And then access the CGI bin directory because you can access it unauthenticated, and accessing CGI bin ML draw, you send a request, and once the Python script will reach the part where it import pylab, it will trigger it indirectly. And I know this is what I was thinking, but if you need it to be composed of two parts, because the CGI bin on one hand is accessible to you, the Python directory is not accessible to you. So if you put the Python web shell inside, let's just say you write the web shell here inside the pylab, ML draw will reach the import pylab, and your payload is executed. You won't be able to pull HTTP information. I don't know how to say this. Like you can't, at least I couldn't do, to reach the request parameters, because eventually you want to get. I mean, yes, you could hard code here something, and it will be executed. But you want a web shell, like you want to arbitrarily execute things that comes from parameters and just use it again. So for that, it's just composed of two parts. The one is a web shell from an accessible path, and the other part is not accessible but can be triggered once. That's a great question, actually. I hope that because it might look silly. Okay, so the full exploit recap. We create a fake table, use it to write file. The first file is a web shell, accessible in an accessible path, which is the CGI bin directory. The second one is a pylab.py, and then we send the request to the ML draw file. This will make our web shell executable. And then we can browse to our web shell and enjoy the web shell. So this is the second demo. So as you can see, in the beginning we are writing a web shell and then creating a chmod gadget. Eventually we are accessing the ML draw, and then we are sending a request to the CGI bin directory x.cgi, which is our web shell, and we get an output of UID, root, GID 0, and group 0. Thank you. Right. So we just covered the second bug. Now I will present to you a tool that I made. It's not a special one, but I like it. The reverse engineering logic that involves custom Apache data structures, specifically Apache, but it can be anything else. It can be, sometimes you reverse engineer a binary that uses a JSON library, and you see random offsets, and you need to go to the sources and understand how the layout is set up. For example, the logic below is a for each loop that uses Apache APR table. The decompilation is messy. It can be painful to manually create structures or import. IDA has a feature to import header files, but it always breaks because you need to fix the include path. So it's not very friendly. And yeah, so here, for example, this part is providing a struct member, the first struct member, and it looks like a dereference. This is 2 dereferences. You have member offsets, more member offsets, but it's arrays, and it's very inconvenient. So to solve that, I created we can call this a database. It's called Symbol Exchange, and it can, just like the description says, effortlessly search for structures, fields, and offsets across thousands of binary packages. And the way it looks like is as follows. You look for the structure that you want to import to your IDA. And then I have a lot of binary packages. It creates Symbol Exchange, like it's create a database with using all these ELF files. It's a lot of ELF files. And it's not just regular ELF files. Those ELF files have dwarf metadata. This is the point of the whole thing. It has dwarf metadata. And it allows you to extract everything, create a database, and even more importantly, let's just say that you find the structure you want to import to IDA, right? All you need to do is just press download. And in IDA, there's a feature of load dwarf file. And you import this ELF file that has debug metadata in it into your IDA project. And everything will be available to you just like that without, like I said before, yes, IDA has this feature. You can do load C header files. But for me, it was just inconvenient because I had to fix a lot of include paths, and depending on what you want to import, which structures, some structures may be not very trivial to import, depend on which library, etc. So yeah, that's really nice that you can have your types in it, and the way that it looks like in practice is like that. This on the left side, you can see that the screenshot from the first from the previous slides, and on the right side, you can see how it actually looks like, what it actually means. And the right side is a lot more, how can I say it, researcher friendly and time saving. So this is something that really helped me because especially in those type of products where there are trivial vulnerabilities, but sometimes when you are required to create types, you can miss a lot of the obvious things, like the out-of-bound read. It was a great example. So that was regarding the tooling, and I think, yeah, this is the end of the talk. It went quicker than I thought. Sorry about that. anyone want to ask any question? Yeah.
How did you stay motivated when things weren't going your way? Like you said that you were just really struggling at the first part when you wanted to work and it didn't. How did you just keep going? Was it just like, were you just stubborn?
Yeah, you go to sleep. What?
Can you repeat the question?
He asked me how do I deal with the part where you are, where you hit a dead end. How do you deal with that? You just keep it aside, continue to do your research, and then hopefully one night you have an epiphany and you run to the computer and and you try your things. But yeah, I don't have a special answer for that. But you just keep just keep it aside. You continue to do your research, and eventually your brain will make up something. Yeah. Symbol exchange. It's like it's a domain. So you can, yeah. I'm sorry, what? Oh, what the patch was? She asked me what was the patch that they did after I reported to them the vulnerabilities. To be honest, it was like, it took them a lot of time to fix it. So the research that I presented to you now is actually 8 months old, something like that. So I don't remember, but from what I remember, it was just the typical things. For example, out-of-bound read, what do? You add bounds check, SQL injection. From what I remember, it wasn't a sloppy fix. It wasn't also the best fix because you saw how this product is made. It was something. I think fair is the word. I'm not sure. Okay, so if anyone else have any question, you can find me in the conference.